Hey, okay, so welcome to the second video. This time we're going to be talking about what's called the principle of superposition. The name sounds a lot cooler than what it actually is. Basically, the idea is that waves have a very unique characteristic uh, that they can occupy the same space at the same time. This is something that particles cannot do. What we mean when we say that waves occupy the same space at the same time is that when two waves interact with each other, they will combine their displacements together to create a new wave, if you will, where they will equally affect the material at the same time. So, for example, let's say two crests come together. You have a 2 centimeter tall crest and you have a 3 centimeter tall crest. Well, when they come together, they'll end up displacing the entire medium by 5 centimeters, a combination of two and three. Um, Now, for mechanical waves, this really only occurs in the elastic region. If you remember when we're mentioning Hooke's law in the first lecture, we talked about how there's the elastic region where it can kind of expand and contract without any issues. Yeah, so this only really occurs during that point. But for example, let's say we have these three waves, one frequency, double the frequency, and triple the frequency, all of different amplitudes. We'd end up getting a complex composite wave that looks like this. So if you pick any point on the wave and you add all the waves up, so this is positive number, this negative number, this positive number, it gets you the net displacement over here. All right. So this leads into what's called Fourier's theorem. Basically, the idea that any complex wave like this can be constructed from various basic sine waves. So you get these sine waves and you have different wavelengths, different frequencies, different amplitudes, everything else, and they'll combine to make a complex wave that looks like this. So that's what Fourier's theorem basically is, that uh, any wave is a composite of and up to an infinite amount of basic waves, if you will. Now, we're not going to talk much about this, but this leads into something with electronics that the idea is that we can actually take these sine curves and combine a whole bunch of different variety of amplitudes and frequencies in order to get various shapes like the square wave, a triangle wave, or a sawtooth wave. Like I said, this becomes something important more in electronics, where certain signals are more important, like a square wave signal is more important, or a triangle wave. Um, this is kind of the math behind it. And this is just an example of what it would look like. So you could take just, let's say, these three waves of, as you could see, various wavelengths and amplitudes, and when you combine them, you'll end up getting a wave that starts to sort of look like a square wave. You know, it goes down, it comes up and flat, and then back down and flat. Of course, as we add more waves, we can smooth this out to get a much flatter signal. One thing I want to point out is in this equation, this K does not stand for wave number. This is just the K that's related to the summation. All right, so interference kind of goes with the whole idea of superposition, the fact that waves can occupy the same space at the same time. With interference, what it's saying is that if we take two waves and they combine, well, they can either create something bigger, which is what we call constructive interference, or they can create something a little bit smaller than their original, which is destructive interference. Basically, it's the difference between adding the waves up and subtracting the waves. Now, constructive interference occurs when the waves are in phase with each other. This means that they're doing the same thing at the same time, while destructive interference occurs when they're out of phase. So here's a good diagram. So these two waves are considered in phase. This one is acting as a crest, just as this one's acting as a crest. And then when they come together, these two crests will combine to make something bigger. And then afterwards, they don't stay together forever. These waves will continue moving past each other as if this never happened. That's one of the other unique things about this is that when they interfere, there's no long lasting effects on them. You know, the waves come in, they combine briefly, they say, "How do you do?" and then they pass through, never to kind of interact with each other again. This is an example of destructive interference. So when we say out of phase, this one is a crest while this one's a trough. When they come together, you get a flat line. And then again, the trough continues moving to the left while the crest continues moving to the right. Now, one thing I did want to point out is um, while this one had them completely destroy each other, it doesn't have to be like that. For example, if this trough was bigger than the crest that came in, then you'd end up with a smaller trough. It's still considered destructive interference. Typically, we would normally call this something like total destructive interference. But yeah, so it would just have to produce something smaller than these two. Now, this is a perfect example. This It's really hard to see this at the moment, but the basic idea is, and you can see this for yourself, when you go into a water, and if you are creating two sources of ripples, essentially, like you take your hand and you try to make a very consistent disturbance in the water to make little tiny waves rippling out like this, what you'll find, these little top parts or these lines in this diagram are representing the crest of the waves. When they start to interact, you'll actually start to see areas where they're constructively interfering and areas where they destructively interfere. It's hard to see in this picture, but the areas where they constructively interfere, where their crest of one interacts with the crest of the other, you'll end up getting the waves becoming a little bit bigger, pretty much almost double the amount, the original. And then you have these areas of destructive interference where it's kind of in between them, where it's where the crest and the troughs meet. And if you're being very consistent with the wave you make, you end up getting these like lines of um, no waves being produced. It's a really cool thing. This picture doesn't really do it justice. You could try it out for yourself. Maybe at some point I might throw up a video and show you guys later on. This is just the whole constructive, destructive, partially destructive example again. So once again, these two waves are doing the same thing at the same time. They add together to get something bigger. These are doing complete opposites. When you add them together, you're really subtracting and getting nothing. Or here where they're slightly off, and then you get something kind of again a little bit smaller. Now, the next few things that I'm going to talk about with waves are going to become much more important in the later section. And by later section, I mean in the third section when we start talking about waves and optics. So reflection is one of those things. So I'm going to mention something very brief about reflection right now, but just make sure that you put a pin in it because, like I said, it's going to become a lot more important later on. So, what we want to talk about is when a wave comes into contact with a boundary, what it's going to do is it's going to reflect back, or part of the wave is going to reflect back. Now, just really quickly, a boundary is defined as pretty much any change in the medium. So we mentioned before about how the speed of the wave will change depending on how heavy or how light a rope is, or how tight or loose it is. Um, Changing any of those two terms changes the medium and it changes the speed that the wave travels through it. So when the wave encounters a section where all of a sudden now there's a speed change, so it goes from a light rope to a heavy rope, and now it's starting to slow down, we call that section a boundary. So that's what a boundary is. It's not like a wall. It's really just more of a speed change from one type to another. Now, if it hits a boundary, it's going to end up, part of it's going to reflect. Now, if the boundary is, let's say, fixed, for example, the rope is on a string, the waves on a string, and at the very end of the string, it's fixed at this end, like tied to something, so it can't move. When the wave comes in and it reflects out, it's going to end up being reflected inverted. One of the things that we're going to call it is it gets phase shifted 180 degrees. This phrase is going to become a lot more important, like I said, in the third section. Now, on the flip side, if let's say this end was loose, so it's tied to something like a ring that allows it to go up and down. Now, when that happens and it gets reflected, it's actually going to stay in the same upright position. Or we can say it's phase shifted 0 degrees, basically saying that's, the same way. Sometimes we call these soft and hard and soft reflections. So when the rope is going towards this heavy section where it starts slowing down, we call that a hard reflection. So that's when it gets inverted. Likewise, if it was going from the heavy section to the light where it starts to speed up, that would be considered a soft reflection, and it would actually remain upright when it reflects back. So, pretty interesting thing. Like I said, this is definitely going to play a lot more importance, especially the phrase hard and soft reflection. Now, we want to also try to take this the next step and say, well, this works fine for a two-dimensional wave where it's only going left and right. But what about a three-dimensional wave? So when we want to think about water waves, so when we go to do that, what we want to do to make our lives easy is talk about plane waves. So as you know, when you have something spherical, when you're like making a wave in a pool, the ripples are going to move out in a spherical circular way, radially outward. Now, as that circle gets bigger and bigger, the curve on it starts to decrease. And when you get sufficiently far away enough, all of a sudden the waves are going to start to look like flat lines, parallel lines. So that's what we're going to talk about is this case. It still works technically for the curves. It's going to make life easy for this, because now what we can do is use straight lines to refer to the wave. So these blue lines, I didn't mention it, but these are supposed to represent the crest of the waves. So like you're looking down on a bunch of water waves, or the ripples in the water, and these blue lines are the crest of those waves. Now the law of reflection basically states that when a wave comes in at some angle, it's going to bounce back at the exact same angle. We call that the incident reflected ray. Like I said, we're going to talk about that in much more detail. But this is why we kind of want to talk about the plane waves, because it makes it a lot easier for us to be able to calculate the angle by making this straight line that goes perpendicular to the wavefronts, and then another straight line going perpendicular to the wavefronts. Now this actually becomes, this is important, the standing wave. So standing waves occur when there's two waves that are interacting with each other, that interfere in such a way that the resulting wave we see ends up appearing motionless. Now what I mean by motionless is, if you think back to some of the diagrams and animations I had for the moving waves, you see that you can clearly tell that the waves are going either left or to the right. Now, for a standing wave, it doesn't work like this. I'm trying to pull up a image, sorry. So it doesn't work that way here. In this case, when the two waves interact, they'll actually result in the waves. I guess I'll just stick with this. They'll cause the waves to do something like this. So the red wave you can clearly see moving to the left. The blue wave you can clearly see moving to the right. These are the two waves that are interfering with each other. But what you end up getting is this black line. This wave that doesn't really look like it's moving left or right. It's just going back and forth, back and forth. Now, this leads into some interesting things. Like, for example, as you look at this, you can clearly tell that we can't really talk about crests and troughs anymore. Like, yeah, clearly I can point that this point on the blue wave is a crest. But if I look at the black line, crest turns into a trough, back into a crest, and trough. So what we want to do instead is replace our terms of crest and trough with the term node and antinode. So the node is going to refer to the point where the standing wave isn't moving. Again, going back to this diagram, we can clearly see these red dots as being the nodes. No matter how this wave travels or goes back and forth, this point stays the same, always. So that's what the node is. You could think of it as being like node displacement. Antinodes, on the other hand, are the complete opposite. They're the areas where it goes the biggest changes. They're the crest that turns into the trough and back and forth. Just make sure that you don't double count. Some people might look at a diagram like this and think that there's 4 antinodes. They'll go 1, 2, 3, 4. No, this entire thing, this bubble is the antinode, or at least the middle of the bubble is the antinode. Now what we want to do is talk about the wavelength and figure out the equation for the frequencies. So this, if we're moving a string, it's fixed at this end and this end. So the only things that could be held at these locations are nodes. So if I'm trying to make a standing wave, this ends up being the biggest standing wave that I can create. It has the least number of nodes, 1 and 2. We call this the first harmonic because this is the first standing wave that I can create. Now, if I want to go to the next standing wave, add in one more node, the standing wave will end up looking like this. So this is called the second harmonic because it's the second biggest standing wave I could create, and so on and so on. So you can actually look, and the first harmonic has 1 antinode, the second has 2 antinodes, and so on and so on. Now, I do want to point out one other thing is we're mainly going to talk about this as the first harmonic, second harmonic, third harmonic. However, this sometimes does have an alternate name. This is usually called the fundamental harmonic. And then this is usually sometimes called the first overtone, as in the first harmonic above the fundamental, or the first standing wave above the fundamental. So just pay attention. Like if you're doing a problem and you're finding that your number for some reason is wrong, but you're pretty sure you're doing all the work, just pay attention to see if they're using the phrase overtone, and you might have to change your number around. All right. So what we want to do is come up with an equation to figure out the wavelength of this. Now, if you remember, a wave has a crest and a trough. So if I'm looking at this, this is just a crest. I know there's a trough underneath, but that's just because that's what it turns into later on. That's like first stage, second stage. So there's only one crest being seen at a time. So this is actually half a wave. So if I wanted to derive the equation, I'd say the length in between the strings is equal to 1/2 of a wave. Now for this one, I could say the same thing. I now have a crest and a trough, so this actually is a full wave. So I could say that the length is equal to 1 wavelength. This is 1 1/2, so I could write it as 3/2. So you should start to notice that this goes up by halves, which makes sense because the distance between one node to the next node is a half. So if I'm going up by the next biggest standing wave, I'm just going to keep adding half a wave to it. So I can come up with a more general equation like this, where I say n is just some number, 1 for the first harmonic, 2 for the second, and so on. And what I plug in, I end up getting, I can use that to figure out the wavelength. And you can see in the first three that it does fit this pattern. Moving the terms around, what I'm going to have is that the wavelength is equal to this, 2L over n. Again, where n is just any positive integer. Now, combining this with the equation for with the velocity equation, we can get an equation for the frequency of each of these harmonics, and I get nv over 2L. Well, if I look back to this, moving this half over to here, I get that the wavelength for the first harmonic is 2 times the length, double whatever my length is. So I can take this 2L and replace this with the fundamental wavelength, lambda 1. Dividing the velocity by that gives me the fundamental frequency. So what this ends up telling me is that each harmonic ends up increasing by this fundamental frequency. So if the first harmonic is, let's say, 5 hertz, then the second harmonic is going to be 2 times that, or 10 hertz. And the next one's going to be 15 and 20 and so on and so on. So once you found the first one, each harmonic is going to go up by that same amount. Now, the one thing I want to mention is that these are the standing waves that could be created. This is the biggest standing wave that I must create, and then this is the next one that I must create. The reason being is I need to satisfy the condition that at these two ends there must be a node. Now, going a little bit more into detail with that, pretty much what I'm saying is that it's impossible for you to have something like this, a string fixed at two ends where a wave goes up and then comes down, but not at a node like that. This is not possible because I need to have a node at this location and at this location. So that's what I mean by the condition is being met. All right, so here's a practice problem. You can work on this real quick and we'll go over it in a second. All right, so what we have here is we're looking for the fundamental frequency. So based off of that, we have these two. Now the key thing is that these two frequencies are successive harmonics. This is Fn and this is Fn plus 1. And as we know, each harmonic goes up by the fundamental. So if I want the fundamental frequency, I'm going to take the difference of these two and get 80 hertz. So that is my fundamental frequency. Now for this one, you can pause the video and work on this yourself. We'll go over it in a second. Alright, so they want to know how far apart the two adjacent nodes are. Well, what I'm going to do is I have to recall that the adjacent nodes, as I said before, are half a wave away. So I need to know what the wavelength is. And based off of what's given to me, I can kind of guess that that's what they wanted me to do because they're telling me velocity and frequency. And in my mind, I should immediately go to v equals f lambda. With a lot of the base equations, the main equations that we've mentioned so far, you really do want to try to get into the habit of recognizing which equations you can use the moment you start to see some of the pieces starting to fit together. So like for example here, you see frequency and velocity, immediately think of v equals f lambda. Alright, so we use that and we find that the wavelength is 0.22 meters. Combining that together, we end up getting that the distance between two nodes would end up being half, or 0.11 meters. Alright, here's the next question. You can pause the video and work on this yourself. We'll go over it in a second. All right, so for this, it wants to know the tension in order for it to create a fundamental frequency of 131 hertz. So let's see, what we have right now is we have the length of the string and the mass. Now the only equation that comes to mind in this topic that deals with tension is V equals rad Ft over mu. So I'm most likely going to have to use that. I can use these two numbers to find the mu, though I'm going to have to be careful with this 9 grams, making sure to convert that to kilograms. The only thing I'm missing is the velocity. Well, what I can use is the length of the string and the fundamental frequency to find the velocity. So I'm replacing mass divided by length in from u, and what I'm going to do, now there's a typo here. These are actually supposed to be lambda 1 and f1 for the fundamental values. But what I'm going to do is put the 131 for the frequency, and this lambda is going to end up being twice this length, because remember, that's what the fundamental is. So putting those numbers in, I end up getting 679 newtons. So that is the tension in the string. Now part B says, what's the frequency of the next 4 harmonics? Well, again, I know that my fundamental, or the first harmonic, is 131, and they're all going to go up by that. So next one's 262, 393, and then 524. All right. Next question. You can pause the video, work on this yourself. We'll go over it in a second. All right, so for this one, what we're going to do is, once again, they kind of give us the answer, so that's pretty nice. What I'm going to do is we're going to use the equation. Clearly, we need to use the V equals rad Ft over mu and combine that with V equals F lambda for this. But we're going to want to try to keep it in variable terms. So for now, what we're going to do is this. So we take the velocity of a transverse wave through a medium, set it equal to the V equals F lambda equation, our main equation, to get an equation for the fundamental frequency. Now, as we said before, any other frequency is going to be some integer number times the fundamental. So we're going to just take this and multiply it by n. Now, I also made a quick little mistake. I was supposed to leave it in terms of L. So, yeah, the lambda is going to be replaced with 2L. Because as we mentioned before, the fundamental wavelength is 2 times the length of your string. All right. This is the next one. So this one is pretty interesting. What we need to do is figure out what frequency will create a standing wave in these two strings. So pause video, work on this yourself, and we'll go over it in a second. Alright, now for part A, it's wondering what conditions are necessary to create a standing wave in both strings. So what it's saying is this. We have two strings. They're both connected to the same, they're both identical strings, and they're connected to the same thing. So they're going to be vibrating the same way. Now, some key things here is they say they're identical linear densities and forces. What that means is their velocities are the same. And because they're being oscillated by the same thing, the frequencies are also the same, which then implies that the wavelengths that are being created on both of these have to be the same. Now, if you recall, the main condition is that the points here at the ends have to be nodes. And then, since we know that they have to have the same wavelength, that means that on this string, it should look almost identical to this up until this location where it ends up being the same length as the first string. So these should have all the same node locations. So if the nodes start at the beginning, this node occurs at 3 meters, this should also be at 3 meters. So our nodes have to be in this location. And then from here, I could say that in within this difference in the length, I can fit half a wave like that, because that's a node and another node. I can fit a full wave like that, or something like that. So basically, I can fit half a wave, I can fit a full wave, or just integer half wave. So that's the condition that needs to be met, is some integer number of half waves. This is going to make our lives much easier to find part B and C. So for part B, it now wants to know what frequency will actually produce this standing wave. Like, what is the smallest frequency? So the way I'm going to do it is I'm going back to that condition that the difference in the lengths between these two strings has to fit half a wave. So from here, I can then combine this with the equations of v equals f lambda, the equation actually pretty similar to the equation that I had previously, using the transverse equation, rad ft over mu, trying to keep it in variable terms for now, mainly because of part C. But what I end up getting is that the smallest frequency is 530 hertz. Now, really quickly, if you didn't see this, it doesn't mean that that's the only way to do it. There actually is another brute force method way of doing this. Basically, what you could have done is use this same equation, but plug in the actual lengths of the strings to get their fundamental frequencies. So for the first string, the one that's 3 meters, it would have had a fundamental frequency of 55.9 hertz, while the next one would have had a fundamental frequency of 54.1 hertz. And then what you could have done is made a list of all the frequencies, all the harmonics that go with this. So for example, this would be the first harmonic, and then the second harmonic would be, let's see, would be 111.8 and then 108.2. And then you could keep going and then find which frequency is the same between them, and you'd find is 530. Now, as you can see, this is going to take a while. I don't know exactly how high we'd have to go. Actually, I can do the math real quick. That would be, yeah, so we'd have to go up to about 9 or 10 harmonics before we get to the 530 hertz area. Now, part C is pretty interesting. One thing I could do is I could redo all my math here and just say, well, the next smallest would be, instead of fitting half a wave, would be a full wave. So I could have done that, basically gotten rid of this 2 factor, and then what turns into the 4, and then redone my math to figure out. Or what I could do is something similar to what I did before and say, well, this is just a full new wave, which is half of the original wavelength. Doing the math, you can actually find that the new frequency is twice the first. Very similar to the way that the fundamental frequency and all the other harmonics were found. So what this kind of tells me is that the frequencies that are going to create standing waves in both strings at the same time will end up acting as this will end up acting as the fundamental frequency for that. So you can almost think of this as being the fundamental shared frequency. That way, the second harmonic shared frequency would be twice the fundamental, or 1060. So pretty interesting result that we end up getting. Now, one thing I want to note here is that while I did put that there was a virus here, meaning that we're not going to talk about it right now, this is extremely important, especially in section 3. Like I said, when we get to that third part, we're going to revisit a lot of the stuff that we talk about waves, but instead of talking about with the mechanical waves, we're going to switch over to electromagnetic waves. So refraction is what happens when a wave enters into a new medium and it's coming in at an angle, and then all of a sudden, because of the speed change, it causes it to switch its direction. So this is the diagram of it. So let's say you have, these are representing the wave fronts. A light ray is coming in. All of a sudden it hits the water boundary, and then it starts to get bent a bit. So a lot of times refraction is also called the bending of a wave. This is just another example of that. Now, the best way to think about this, if you want to try to like visualize what's going on, you could think about a cart traveling, like a grocery cart, if you will, traveling along a concrete road. All of a sudden, when it comes into contact with a grass surface, a surface where it's not going to move as fast, the moment one wheel hits, like if one wheel hits the grass first, that wheel is going to slow down, but the other wheel is still on concrete, so it's gonna maintain that fast speed. Well, if one wheel slows down and one wheel speeds up, then all of a sudden it's gonna switch and swerve towards that slower wheel. So that's what's going on here. The one wheel hits the slow grass, the other wheel is on the fast concrete, and it causes it to swerve towards that slower direction. So this is just a brief explanation of how this equation can be derived. Basically saying that you can get a relationship between the velocity and sine of the angle that it either comes in or leaves at. Basically that those two are directly proportional. But like I said, we're probably not going to end up using that. Diffraction is another one that is going to play a much bigger part in the third section. Basically, the idea about refraction is that when a wave comes towards an obstacle, it's going to end up bending around it eventually. That's what diffraction is. So the best way to put it is the fact that there will exist behind an obstacle a shadow, where in that shadow region the wave does not interfere. It does not go over there. So in this picture you have like a block, and it's being exposed to water waves. There is a shadow behind it where the water waves will not reach. So you can see the waterways are being blocked in this location. But as you get further and further away, just like a regular shadow, it will eventually get smaller and smaller until the waves do finally go around it. So essentially the idea is saying that because of diffraction, the shadow region is not infinite. It is a finite region. Now, depending on how big the obstruction is compared to the wavelength, the spreading is going to be different. So, for example, if the wavelength is very small and the obstruction is really big, there's not really going to be much spreading. Here are some other examples. Like, for example, this is a very small obstruction with a very big wavelength. So the spreading is going to be so big that there's almost a negligible shadow region. And then same thing over here. Small object, big wave, very small shadow region because the spread is so big. But here we have a small wave and a big obstruction, the shadow region's much bigger because the spread is much smaller. So it's going to take a lot longer before it goes completely behind the obstacle. This is just a relationship that relates the spread of the wave to the wavelength and the length of the obstacle. Like I said, though, this becomes a lot bigger in the next part. So these are the things that we've talked about. We talked about the whole wave condition. You know, that equation that tells us whether or not the one of the equations we have to describe a moving wave is actually a viable equation. We talked about a good solution to the traveling wave equation. We've also talked about some things, some terms like the angular frequency and wave number terms, as well as a little bit about standing waves. And we even talked about how waves interact with boundaries. So the whole idea of reflection, refraction, interference, diffraction, all that good stuff. So this is the homework, chapter 15. It's going to be due Friday. Those are the questions. Really quickly though, for question 18, it is a typo. It says joules per meter squared, but it's really supposed to be watts per meter squared. I don't know what happened. They might have changed the phrasing a little bit, but it's supposed to be watts per meter squared. All right, so that's about it. You can watch the video where I go over the extra questions. Otherwise, I'll see you later. Have a great day.